record. Okay, all right. So last time, which is now 2 weeks ago, we started sets, right? Basic set theory. And so we saw the basic definitions of sets and the basic operations on sets, union, intersection. So I'm assuming you're familiar with this. So next topic is just some very, very basic counting techniques, extremely basic. Let's just define what we mean by cardinality of a set. So if you have a set which has k distinct elements, or k is a non-negative integer, could be 0, okay, then we say that the set has cardinality k, and it's finite, otherwise it's infinite. And the notation for cardinality is exactly like you see on the screen. So 2 vertical bars, or n of a is equal to k. So that's the number of elements in the set, okay? Obviously, a set has 0 elements precisely if it is the empty set. That's the only set with 0 elements. And as you know, the set of natural numbers, integers, rationals, real numbers, these are all infinite sets. What you might not know, but is useful in computing for sure, is that the set of primes, of prime numbers, is also infinite. This is a very, very old result that's in Euclid's Elements, but we sort of use it indirectly because in public key cryptography, we need really big prime numbers. And so we're happy that there are infinitely many, so we can find bigger and bigger ones to make the codes harder and harder to break. But that's another story. Okay. All right. Okay, from this point on, the sets we're going to look at are finite. Okay, so infinite sets don't come into play very much with computers. Everything is finite in computers. So our first obvious fact is that if you have 2 sets which are disjoint, recall that 2 sets are disjoint if their intersection is empty, they have no elements in common. So if you want to count the number of elements in the union, all you have to do is add the number of elements in A and B, right? So the number of elements in the union of A and B is the number of elements of A plus the number of elements of B. I think there's a plane outside. I don't know if you can hear that, but yeah, anyway. Okay, so this is an obvious fact, right? Here's a slightly less obvious fact, which I'm going to call inclusion-exclusion for 2 sets. So why am I giving this not so difficult result such a fancy name is because we're going to see the same thing for 3 sets in just a minute, and it's a bit trickier, okay? In fact, you have a formula like this for any number of sets, but it's quite messy, okay? We're not going to see it for more than 3 sets. But let's take a look at it for 2 sets to start with. So basically what we want is an alternative way of counting the elements in the union of 2 sets, okay? I mean, obviously, if you know the sets, you can just count the elements, right? But sometimes the number of elements can be the elements can be presented in a weird way, and this can be a useful way of counting these the number of elements in the set. So we have 2 sets, A and B, and we want to count the number of elements in the union, okay? So here's a way of doing it. So this is equal to the number of elements in A plus the number of elements in B, but you need to subtract the number of elements in the intersection. Okay, so what's the logic behind this? It's actually pretty straightforward, okay? So let's do the following, okay? Again, I'm doing this on slides. If we were in class live, I'd be writing on the board at the same time, which is technically difficult for me. I realize I haven't found a good way of sharing 2 screens yet. So bear with me. I'm sorry. I might try to do something a little later on writing, but anyway. So So I'm going to count the elements in the union of A and B as follows. So first, I count the elements which are in A. So I get n of A of these, right? Then I count the elements which are in B. I get n of B of those, okay? So I've counted a total of n of A plus n of B. But I might have made a mistake, right? Because there are some elements which I might have counted twice. Which are these? These are the elements which are in A and in B. Sorry. Okay, so if an element is both in A and in B, I've counted it twice because I counted it when it was in A and I counted it because it was in B. So what I do is I subtract those because I counted them twice. That's where the formula comes from. Hopefully that makes sense to you guys, right? So I'm counting the elements in A, counting the elements in B, and I've counted those which are in both sets. I've counted them twice, okay? So I remove that. That's where the formula comes from, okay? So let me show you an example, very simple example. Okay, so A is the set consisting of the elements 1, 2, 3, 4, 7, 9, 10, and B is the set consisting of the elements 2, 3, 7, 8, 10, and 11. Okay, now you can see that A has 7 elements and B has 6 elements. And if you look at the elements that they have in common, there's 2, there's 3, there is 7, and there's 10. So that's 4 elements in common. Okay, so my previous formula says that the union of A and B should contain 7 plus 6 minus 4 elements, which is 9. Okay, and if you look at the union, if you take the union of these two sets, it consists of 1, 2, 3, 4, 7, 8, 9, 10, 11, and that's a set with 9 elements. Okay, so that illustrates what I was talking about. Okay. Hopefully this is okay for you guys.
I mean,
Okay. Yeah.
picture representation would have been a lot better for those who don't know.
Yeah, I
If
know.
anyone's if anyone still doesn't understand, I mean, it's pretty simple.
Yeah.
I
I
mean,
mean,
technically, if you have a Venn diagram, you just remove the intersection or the between section.
yeah, intersection. Yeah. So I'm gonna use the iPad in just a minute to do an example, and yeah, I'll illustrate it like that. Absolutely. Okay. Let's go to 3 sets, which is slightly trickier, but it's the same idea. Okay. So the name inclusion exclusion is exactly this, is that you're including some elements and then excluding some because you've counted them too many times. Okay. So here's a formula to count the number of elements in the union of 3 sets. Okay. So I have 3 sets A, B, and C. And I want to count the number of elements in the union of A, B, and C. A union B union C. So the formula says this is the number of elements in A plus the number of elements in B plus the number of elements in C. Subtract the number of elements which are in A and B. Subtract the number of elements which are in A and C. Subtract the number of elements which are in B and C. And then add back in the number of elements which are in A and B and C. Okay, so what's the logic behind this? Again, so here's the argument. Okay, so I look at all the elements which are in the union A union B union C. I do this. I count the elements in A. I count the elements in B, and I count the elements in C. But now think of the elements which are in both in A and B. I've counted them twice, right? So I remove 1 for each. Same thing for the elements which are both in A and C. I subtract 1 for all of those because I've counted them twice. And I do the same for the elements in B and C. But now, if you think about it, now you've subtracted 1 too many times for the elements which are in all 3, right? So if an element is in A and B and C, you've removed it 3 times, once for A and B, once for A and C, and once for B and C. So you haven't counted it, so you add it back in, okay? So that's the idea.
Are we gonna do 4 sets or no?
No, 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 no.
Okay, because it's a huge nightmare, and I was really wondering if we're gonna do
I
4.
mean, the principle, the
It stays
one,
the same.
it's the same, but the formula gets really very nasty to write down.
It gets annoying.
Yeah. Okay. So no, we're not going to go further than 3 sets. Okay. Now I'm going to show you a very typical example of how this is used. Okay. This is not a hard problem, but if I gave the problem to you without you seeing this before or never practicing it, you might get stuck on it. Okay. But once you've seen this and you've done a few examples, it is not difficult. Okay. So here's our example. So there is a college called a college with 3 L's. I need to fix that. ABC College has 120 mathematics students, and 100 of them take at least one course in French, German, or Italian. And then we have the following numbers. We know that 65 of them study French, 45 of them study German, 42 study Italian, 20 study French and German, 25 study French and Italian, and 15 study German and Italian. Okay, now we're asked how many students study all 3 languages and how many study only Italian. Okay, so the questions there are, they could be different. Okay, so what we're going to do basically is figure out exactly, precisely the number of students which study exactly 1, exactly 2, exactly 3, and all this. Okay, and it's not super difficult. Okay, there is one thing you should never mess up. Look at those numbers. Okay, we have 120 students total. Look at those numbers there: French, German, and Italian. 65, 45, 42. If you add those up, that's way more than 120, right? This should be clear. Okay, so don't mess that up. So obviously here we're counting the same people several times here, right? So just please keep that in mind. Okay, this is a common mistake. Okay, so let's take a look again. If I had another board, it would be really cool. What I'm going to do is, okay, let's see what I can do with this. I'm going to, okay, I'm going to start on the slides and then I'll switch to the iPad. I'm just going to write down immediately. So 65 French, 45 German, 42 Italian, 20 French and German, 25 French and Italian, 15 German and Italian.
It's kind of funny. I had this exact same question back in secondary 4.
All right.
On the exam, I had the exact same one. It
Yeah.
didn't change whatsoever.
Okay. All right. So, okay. So let's go take a look at this. Okay. Oop. So here's a picture of what we're looking for. So I've drawn a Venn diagram. Okay. The rectangle is your universe, or all students or mathematics students at ABC College. Okay. And we have 3 circles representing students which study French, German, and Italian respectively. And I want to basically figure out how many students are in each of these regions where the question marks are. Okay. So first of all, we're told that there are 120 students and 100 of them take at least French, German, or Italian, right? So that means that there are 20 who do not study any language. So that's 20 right there. Okay, you see that there are 20 students which are outside these 3 circles, outside the union, right, of these 3 sets. Okay, so there are 100 in the union, so 20 outside. Okay, the first thing I'm going to figure out is that number of students right in the middle, okay? So my inclusion exclusion principle is going to help me figure out that number. So what's the inclusion exclusion principle? It says this, okay? It says that the number of students in the union, how do I count that? It's the number of students in each one of the classes, subtract the number of students that take 2, and add back those that take 3, okay? So I've got all the numbers here, and I just basically just replace everything that I have. So the number of students that take either French or German or Italian, some language is 100. I was given that. The number that take French is 65. Number that take German is 45. Number that take Italian is 42. The number that take French and German is 20, and so on, right? Okay. So, sorry, I need to.
Just to be sure, sir.
Yes.
Whenever you're given an exam with this, like with this in general,
Yep.
will we at least have the like what do you want to call them? Keep forgetting the word for it. Will we actually have like the work or like the formulas given? The formulas?
No, not that. I mean,
Not this.
there's. I mean, you just like have about 12
No,
things to know for the whole
yeah,
course. So no, I'm not gonna give it to you. No.
Okay, it's because I don't know. It's because back like in high school, we were always giving it to us, and we were never
Yeah, but
really forced to like remember it.
no, but yeah, no. The here, I mean, no. This is like no. There's no point if I give you this. No, you should to understand it. You'll remember it, right? There's
I mean,
nothing to
yeah
memorize.
and no. I don't know. It's just I guess the order per se.
Yeah. No, that's you'll be okay. You'll be
It's because
okay.
we were always giving it to us, and I don't know why.
Well,
We're like I don't know. We were always giving it, so it's like
so
even during the final exam.
in the context of the high school, I mean, in the context of a high school math course, it's the whole year, right? So you had 10 months of math. So that's one little itty bitty thing. But now we're doing a course which is 15 weeks, which, yeah. So no, it's the context is a bit different here, and you're in CJEP, not in high school. So, yeah. All right. Okay. So I've got my equality. And you see that the only unknown in there is the number of elements in F intersect G intersect I. So I can just solve for it, right? Simple arithmetic here. And you'll find that it is 8. You just solve for that and you find that it's 8. Okay, so I found my first unknown, which is right here, which is 8. Okay, so now I'm going to switch to the iPad for a sec so I can show you what I'm going to do. Let's share this. All right, so I found 8 here. Okay, and now, damn, was this? I hope this was French, German, Italian. I want to. Let me just check.
Yeah, it was.
Yeah,
I have it written down.
Okay, good. So now what I'm going to do is I'm going to work from the middle towards the outside. Okay, so let's just take a look at this part here. I'd like to know the number of elements of people here. So this total region here is the students studying French and German, right? And I know that the total number of students studying French and German is 20. So that means that in this region here, I must have 12 students, right? Because it's 20 total in the whole thing here, okay? So here's what I'm gonna do. I'm gonna put that in yellow here. And
sir, are you using Notability app?
Yep. Okay. Next, I'm going to look, let's change our color here. So let's take a look at this part here. This is Italian and German, right? Right here. So I've got 15 students studying Italian and German. I've got 8 in here, so that leaves 7 here, right? And finally, let's use green. This part here, that's French and Italian right here. Okay, I've got 25, so that means I've got 17 here, right? So you have a total of 25 here, 20 here, 15 here, and the numbers are correct. Okay, next, I want to know how many students are here. Okay, so I know that I have, let's take a new color. I have 65 students studying French total. Okay, here I've got 17, 8, and 12. So that's 37. And if I subtract 65 minus 37, that'll give me 28, unless I messed up. So that would be 28. Does that make sense? Hopefully it does. I might cheat. No, I'm not going to cheat. We'll see how it goes. Okay. The thing is that you can really check your answers at the end. It's very simple once you have all the numbers. Okay.
You just add them all up.
Exactly. Yeah. So you can check. You have all the information basically. So you can always work back up to check everything. Okay. Let's figure out. Let's say this is dark blue here. How about this one here? Well, I've got. This is the number of students studying German. There's 45 total, but here I've got 12, 8, 7, so that's 27, and I've got 45 total, so 45 minus 27, that's 8, that's 18. So this should be 18. If you see me make a mistake, just tell me. Okay. And finally, let's do that in pink. I've got 42 students in Italian.
You should have 10.
Let's see. 17, 8, 7. So that's 32. After 42, yes, that'll give me 10. That should be 10. Okay. So you see how I work back up. So again, I figured out, oops, let's not write that in pink. I figured out how many students took all 3 languages, and I could get that from the inclusion-exclusion principle, right? Because I had the number of students in the union and in each of the intersections 2 by 2 and so on. So I could figure out how many students took all 3, and from that number, I can go work my way back up and get the numbers in each section. And now you can check, right? So if you add all the numbers in the French here course, you should get the total, which is 65 if you add them all up. But of course, we did the computations correctly. We know it's going to work out. But so from this, you can get all the numbers back. Okay. So let's go back to okay. Do you guys see the PDF? Yeah.
Yes.
Okay. So that's exactly what I did, right? So here's all the explanation. I said, since 20 study both French and German and 8 study all 3, there are 12 left, and so on. This is the analysis where I found the numbers here, like that. So I guess I got everything right. Good. Okay. All right. So most examples are exactly the same. So it's again, it's always with the inclusion-exclusion principle, you find how many whatevers are in the intersection of all 3 sets, and then you work your way back up to find all the individual values. Okay, so it's not too hard. Okay. Any questions on this up to this point? Because I'm done with the counting part. That was it basically.
Yeah, just about sharing two screens at the same time. I mean, you could just in the green, top left, where there's a green, you can just put that tile on the left and then open up a second the other one that you're writing, simply notability, I believe.
I'll try that. I tried a couple of times and it didn't work out very well. I don't see I mean, I could only share one thing at a time for some reason. I'll check it out after. Thanks.
My
Okay.
pleasure.
All right. So let's hide this. Let's go here. Okay. Next topic, relations. So the point of this is just to base some very basic definitions. Again, there's no deep concepts here. There's just basically just definitions. These are concepts which are very useful in databases. And also, if you do any sort of elementary probability, this is always used all the time. Okay, so again, if you remember when I defined the notion of set and the notations for set, when we write down the elements of a set with the curly brackets, the order of elements does not make any difference. So if I write curly bracket A comma B or curly bracket B comma A, it's the same set. It's the set that contains the elements A and B. That's it, okay? But I'd like to consider the case where the order actually matters. So these are called ordered pairs, okay? And we use just the normal round brackets for those, okay? So an ordered pair of elements from a set S, okay, is a sequence of two elements A and B from S, and we use those round brackets, normal round brackets, to indicate that the order matters, okay? So the pair AB and the pair BA are different, okay? You could do this for 2, for 3, for 5, for 1 million. Okay, we'll mostly look at 2 and 3. Okay, so these are ordered pairs. Cartesian product of sets. So this is a new operation on sets, but we're not going to play much with the actual product itself. It's just there to talk about the collection of ordered pairs. So if I have two sets A and B, their product, which is denoted in the obvious way A product B, this is the set of all ordered pairs where the first component comes from the set A and the second component comes from the set B. So it makes a difference, right? So A times B is the set of all pairs little a, little b, where little a comes from big A and little b comes from big B, okay? So we have an example here where if the set big A is the set consisting of 1 and 2, and big B is the set consisting of X, Y, and W, then A times B has for its elements the pairs 1X, 1Y, 1W, 2X, 2Y, and 2W. So there are 6 pairs in this product. Okay. So notice, and this is important, that A times B and B times A are not the same. They contain different pairs, okay? So for example, if you look at the pair X1, it's in the set B times A, but it's not in A times B, right? Because you can't flip the pairs. If you see A squared like that, and A is a set, that means A times A, okay? It's the set. Okay. All right, so here's a couple more examples. So I have the set A consisting of 1, 2, set B consisting of X, Y, Z, then A times B is the set consisting of all the pairs 1X, 1Y, 1Z, 2X, 2Y, 2Z. A squared, that's A times A. These are the pairs 1, 1, 1, 2, 2, 1, and 2, 2. B squared will have a whole bunch of pairs. So you take all the pairs where each of the two components comes from B. So you got x, 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 y, x, z, y, x, y, 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 z, z, x, z, y, and z, z. All right. Now, if you think about it just a little bit, you will convince yourselves that the number of elements in A times B is the number of elements in A times the number of elements in B. Okay, that's not too hard to see. Okay, so far so good. All right, we can take products of 2 sets, but we can take products of 3 sets. Okay, so if I have 3 sets A, B, and C, the product A times B times C is the set of all ordered triples, little a, little b, little c, where each entry comes from the correct set in that order. Okay, so for example, if big A is the set consisting of 0 and 1, and big B is the set consisting of the elements 1 and 2, and big C is the set consisting of the elements 0, 1, and 2, then A times B times C. So you list all possible triples where the first entry is either 0 or 1, the second entry is 1 or 2, and the third entry is 0, 1, or 2. So you look at all the possibilities, they are listed there. I'm not going to read them out, okay? And again, you can convince yourself probably that the number of elements in this product is the product of the number of elements in each set. Okay, so here I had 2 elements in A, 2 elements in B, and 3 elements in C. So the total number of elements in the product should be 2 times 2 times 3, which is 12, which is exactly what you see there. Okay. All right, so of course it gets really big, obviously. Okay, so what's a relation? So again, this is just a definition, okay? So a relation from A to B, where A and B are sets, is any subset of A times B. Now, if you start thinking about how many relations there are from A to B, there's a whole bunch of them. I mean, if A and B are fairly large, this gets really big, okay? So any subset of A times B, we call a relation from A to B, okay? More notation, we say, in terminology, we say that little a is related to little b when the pair AB is in the relation. And we also write A, R, B, A related to B, okay? And if A is not related to B, it means that the pair AB is not in the relation, and we write A, not R, B, okay? So here's an example. I took 2 sets. A is little a, little b, little c, and big B is 0, 1, 2, 3. And I just took one possible relations. There are a very large number of them, okay? I took the relation which consists of the pairs A0, A1, A3, B1, B2, C0, C3. That's one relation. I mean, it's just a bunch of pairs, okay, in A times B. So you see that A is in relation or is related to 3 because A3 is in that relation, but C is not related to 1 because it's not in R as listed, okay? So it's just it seems arbitrary, but it's an extremely useful concept. Okay, I'll try to show you a more concrete example. Here we are. Okay, so when you have relational databases, you have like what's a database? It's basically a bunch. Yep.
I was just going to ask you to go back for a little bit because I haven't finished copying the example down.
Okay. Okay.
Okay, thank you.
Okay, great. Okay, so what's a database? I mean, simply put, it's a bunch of relations. That's what a database is. Okay, and I'd like just to illustrate this a very, very simple-minded example. Okay, so let A be the set of all cities in Canada. Okay, which, I mean, you could add that they have an airport. Otherwise, it's not really interesting. But and let B be the set of cities, all cities in the world. Again, could be airports. And I'll say that little a is related to little b if there exists a direct flight by Air Canada from city A to city B. Okay, so that's a relation from A to B. Okay, so for example, Montreal, Frankfurt, that's in my relation. It's in my relation, right? Because there is a direct flight from Air Canada from Montreal to Frankfurt. Yeah, still even today. Yes. Toronto Paris is also a pair in that relation. So Toronto is related to Paris. Montreal Rio, no, it's not. There's no direct flight from Air Canada from Montreal to Rio in Brazil. Joliette Bruxelles, no, there's no direct flight from Joliette to Bruxelles by any airline actually. so it's not in there. Okay, so simple, very, very concrete, simple example of what a relation is or how it might be used. Okay. All right. Finally, representations of relations. I'm going to show you 3 ways of representing relations. And again, there's nothing deep here. There's no deep math. It's just very, very basic definitions. So there are 3 sort of standard ways of representing relations. The first one is sort of meh. The next 2 are really, really important. So let's start with the first one. Okay, so I'm just basically gonna play with an example, and you'll see how this works. So I have 2 sets, A and B, as usual. A has elements A, B, C, and B has elements 0, 1, 2, 3. So I can depict the product A times B, a little bit like the real plane, right? It's a sort of the same idea, except here we have just finitely many points. So you see that on the horizontal axis, I have the elements from big A, little a, b, c. The vertical axis has the elements from B, 0, 1, 2, 3. And the points that you see, the 12 points there, are the elements of A times B. Okay, so like the pair C2 is depicted as you can see in the picture. Okay, so now I can depict, using this idea, I can depict any relation from A to B simply by looking at the points in the relation. So here's an example. Okay, I take the relation A0, A1, A3, B1, B2, C0, C3. That's one possible relation from A to B. So I depict it in the diagram simply by putting the dots where the pairs are, the pairs which are in R, right? So you see that there are 1, 2, 3, 4, 5, 6, 7 pairs in that relation, and they're depicted there. So if you see that picture, you know what the relation is, and you see the relation, you know what the picture is. So these are 2 different ways of representing your relation, okay? I mean, it's one way of representing the relation as written down, okay? Again, this is not like, I mean, this makes sense, but it's not the most important of the 3 ways I'm going to show you. The next 2 are a bit more convenient or used. So this one, this is, I mean, unfortunately, so I'm showing you this definition and we'll never do anything with it, which is a bit silly, but okay, that's what I have to do. But digraphs are like super useful in computer science. So again, but yeah, here we have a special case where the 2 sets A and B are the same. So I have a relation from a set to itself. Okay, so So you don't cover all possible relations this way, special kinds of relations, but this is a very, very useful way of writing down relations of this form. Okay, so I have A equals to B. I'll just call it A, of course. And I have a relation R from A to A. So these are pairs of elements from A. Okay, so I can represent this as what is called a directed graph, or digraph for short. Okay, so the elements of the set are points in the plane. Like in the picture you see 1, 2, 3, 4 there. My example has 4 elements in the set A, 1, 2, 3, and 4. So these are points. And if a pair is in the relation, let's say AB, I put an arrow from A to B. Okay, so you can think, I mean, think of the, airline relation that I talked about earlier. It wasn't the same set, but you could do it on the same set if you wanted to. And you'd get arrows from one place to another if there's a direct flight from Air Canada from that city. So makes sense. So the example that I have here, the relation I took is 1, 2, 2, 2, 2, 4, 3, 2, 3, 4, 4, 1, and 4, 3. So I have an arrow for each one of these pairs. So I have an arrow from 1 to 2, 2, 2. So I have what we call a loop. There's an arrow from 2 to 2. There's an arrow from 2 to 4, 3 to 2, blah, 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 and so on. Okay, so you see that you have a representation of your relation as a picture, right? So you can read off various properties of the relation very quickly. Okay, so so that's one possible way of representing a relation, as long as the relation is from a set to itself. Okay. Finally, the last way of representing a relation is very useful, because in particular in machines, that's usually how we represent relations, as a matrix or an array of bits, zeros and ones. Okay, so we talked about this a couple of weeks ago, something very, very similar. So let's say that I have two sets, A and B. So here A is consists of the elements 1, 2, 3, B consists of the elements U and V. And I took the relation which has 3 pairs, 1U, 1V, and 3U. So I have an array, and what I do is, so on the horizontal, so the horizontal line, I have the elements from B, vertical, I have the elements from A, although this doesn't really make a huge difference here. It's a matter of convention. But in any case, I have an array where each entry corresponds